Hello, everyone. We are going to keep going with Unit 2 material. We've got some more info on systems of objects today. We'll look at how to start solving problems using Newton's second law of motion for systems. And we'll get to a particular type of systems of objects, which is Atwoods machines. And that's what we've got planned. All right, so we will get into it. We're going to start with some overall information about systems and how to work with them. Then we'll do some application of that for a basic example of a system of objects. Then we'll go specific later on with Atwoods. So we're going to start with solving problems using systems of objects. So for any system of objects, keep in mind just from last time, this was a system of objects would be like two or three things that are often connected in some way, like they might be tied together with a string or three blocks that are stacked on top of each other. Um, Later on in Unit 3, the system, it won't be as important that they're like connected, but with forces, we tend to have um, two or three things that are like, yeah, connected in some way. So for any system of objects, it will become important. So um, it's important to distinguish between internal and external forces uh, acting on the system and the objects within it. Okay. Um, so we're going to go ahead and define those. We're going to say what are internal and external forces. So we'll do that here. And then I'll give some examples of this. We'll talk a little bit about how we see internal and external forces show up in some of the systems we could see around us. So internal forces are forces acting within oops, within the system. And we could sort of reword this again and say forces acting within the system. One object in the system acting on another object in the system. Okay, that's internal forces. So when you have a system of objects, if there are forces acting within the system, one object in the system pushes or pulls on another object in the system, that's internal. External forces, probably could guess what this is. This is forces acting from outside the system. And these forces acting from outside the system are either acting on the system as a whole, or we could say on objects within it. Okay, cool. So let's talk a little bit about um, this in terms of what we've done already. So we might say a box experiences a force. Maybe you're lifting a box or it's sitting on the table or whatever's happening to it. There could be stuff in the box. We don't know. Maybe there's some books in the box. If there are, we consider the box as just one thing, right? None of our problems have in none of our problems so far have we gone in and looked at like specific masses of like books within a box. If the box is full of books, we would just say this is a 47 kilogram box full of books, and that's just our object. But we know from systems that we could also view that as the box and the books are a system of objects made up of all those individual objects. So internal forces would be the books pushing or pulling on each other. So there's forces like if three books are sitting on top of another stack of books, then those three books on top are putting a force on the books below them. And there's lots of pushing and pulling between the objects in that system. But we don't use that really to look at what happens to the box. Instead, we say, well, what is the force of gravity acting from outside of the box of books, acting on this whole system, which is the box and all the books within it? You could even go smaller and say the books themselves are a system made up of pages, right? The cover of the book is an object. The pages themselves could be objects. You could consider that a system made up of objects. You could go smaller with molecules, and molecules are a bunch of, well, we don't really call molecules objects, but you get the idea. You could break things down into systems, and you could take something we'd normally treat as an object, like a pencil, and say, well, there's still parts to that pencil. There's still smaller objects within it. So you can always make a system out of something. But the reality is, when we look at something in physics to do a problem or solve something, we tend to not look at those internal forces. We tend to really not spend time on that. So that's going to be important. So let's make some comments here about using internal versus external forces. Whereas the external forces are the things we care about, right? That box of books example, gravity acts from outside of the box, pulling on it, pulling it down. The table that it's sitting on pushes upwards on the box of books with a normal force from outside of that system, which is the box and the books. So external forces we do care about. Those are what we really account for. Internal forces, not so much. So when we're using Newton's second law, which we're going to be doing quite a bit, to analyze systems and objects. Um, we need to only include external forces in the equation or in the sum of forces, not internal forces. And this actually applies to the stuff even outside of systems. If we looked at like a pencil, because I gave that example, you could say that pencil has internal forces within the object itself because, oops, I did not mean to do that. Trying to erase part of this. Never mind. I'll just leave it. Oh boy. All right. So with the example of a pencil, right? You could look at the forces of gravity or normal force or applied force if you're picking up the pencil or friction if you're sliding it on the table. Those would all be external forces, right? The earth acts from outside the pencil. The table for friction or normal force is outside of the pencil itself. Your hand providing applied force is outside of the pencil. So we already do this. Internal forces are not included when we do a sum of forces. So that's a key thing here. Internal forces would be something like the molecules within the pencil exerting forces on each other to hold it together. The glue that holds like the eraser onto the pencil as part of the pencil itself. That's an internal force. So there are forces going on within the pencil itself, but we don't look at those when we're thinking about the pushes and pulls that act on an object and the resulting acceleration of the object or something like that. Okay, so internal forces not included, external forces, those are what we're interested in. So what this means is, and how we further apply it to systems, is we have the option of using the sum of forces equation. So we can use sum of forces equal to mass times acceleration, Newton's second law, for the system itself. Or for each individual object or for individual objects within it. In a little bit, we'll do an example that shows this. We'll show exactly what we mean by this. But the basics are, you could consider what are the external forces acting on my entire system, and I'll go ahead and sum those up and use sum of forces, mass times acceleration, work with that. Or I could pick one object within the system and say, I want to look at this object specifically. Let's consider what are the forces acting on this object. I want to do a sum of forces and look at the acceleration or the forces acting on this particular thing. So we can do that. Okay. There's another really key piece here is for connected systems, where you've got like a bunch of blocks tied together with a string, where they're all stacked up on top of each other or next to each other. The acceleration of a system will be exactly the same value as the accelerations of all objects within it. We'll explain this further in a little bit with a nice example, because we'll show that if the whole object, or the whole system accelerates at 2 meters per second um, squared, then everything within that system must also be accelerating also at 2 meters per second squared, because we can't have parts of the system that are accelerating more or less than this system that's all connected and sort of moving or accelerating as one. And yeah, we'll get to visualize that here in just a second. Okay, so we're going to draw, at this point, we've got an understanding of, okay, what forces do we want to include in our sum of forces, external? What forces do we not want to include? Internal forces. And then we know now that we could sum forces, we could look at the entire system, or we could go and pick out individual objects within it. It turns out you could also do combinations. So if you had 3 objects total, you could also combine 2 objects out of the 3 into sort of their own little system, and you could look at that for the sum of forces. So there's plenty of options here, lots of ways that we could go with it. But let's set this up and let's kind of do an example. So I find this probably best as like I'm going to use some numbers and we'll actually just solve for some things. So I'm going to have a little system here. In fact, I'm going to make a very nice flat line for my floor. This here. Okay, and we're going to do 3 objects. We'll have object number 1 right here. Object number 2 right here. Object number 3 right here. And we'll give them some masses. The first one's going to be the smallest, then medium, then big. This will be our 1 kilogram mass. This will be a 3 kilogram mass, and this one can be 5. And we're going to connect them all with some string or rope. So we get one here, one here. You might also see systems where all 3 of the blocks are like pushed up against each other, because that would also, if you stacked them up end to end and you put them all right up next to each other, and then you pushed or pulled on one of them on the end, like you pushed the 5 kilogram to the left, or you pushed on the 1 kilogram pushing to the right, you would get all 3 of them to slide together across the table. So that's also an option. Okay, so we've got some ropes connecting them, and what we're going to do is we're going to start looking at forces that are acting, and and we'll think about like how would we solve for, and we'll establish what we're going to find. What we're going to do is we're going to find the acceleration for all objects and the tension in both ropes. And we're going to start with one piece of information besides the masses, which is how much force. We're going to go ahead and pull the 5 kilogram this way with 20 newtons of force. All right. I think we are all set up. In fact, I'm going to change this number a little bit, make it a little more convenient. We're going to do 18 newtons. Sorry about that. Cool. So this 18 Newton force it could be an applied force. It could also be tension. Maybe we attached a string to the object. Now, we could go one by one and draw free body diagrams. In fact, as we go through and solve, we will do that. But I'm just going to start with this whole picture here and just start drawing some forces as well, which is not technically a free body diagram, but we're going to start depicting some of the forces here so we can start picking through internal, external forces, etc. All right. We can, of course, identify gravity as a force that's acting. So we've got 50 newtons of gravity here. I'm realizing that my drawings are very much not to scale, so we'll just do our best with it. Make that one there. 50 newtons of gravity. We should probably pick directions as well. So we're going to have positive right, positive up. Move this over a little bit. Okay, so this would be negative 50 newtons. And we could label this as a force like Fg. I'll do Fg3 because it's the third object. The second object over here also has a force of gravity. Not perfectly to scale, but maybe make it a little bit larger. Not quite as big as the other one. Oh. I was trusting myself to draw straight lines. Apparently that's a challenge for me here. That's better. All right, that'll work. Negative 30 newtons. Now, remember how I'm getting these numbers so easily. You're like, how is Mr. Barros just figuring out all these forces of gravity? Well, the force of gravity equation is a pretty nice, quick one. You simply take the mass of the object times the acceleration of gravity on Earth. So you can just take your mass times 10, and that is something that AP will expect you to be able to do. On all problems, they expect if they give you the mass, you immediately should be able to find the force of gravity on that object, which on Earth is pretty simple. It's just take the mass, multiply it times 10. They expect you to do the reverse as well. If they give you a 30 Newton force of gravity or negative 30 newtons, they would expect you to be able to know that the mass of that object is 3 kilograms. So luckily, it's going between the force of gravity and the mass of the object is not too bad, but they will expect you to be able to do that quite fluently. Last one here, there's another force of gravity there. That's just a negative 10 Newton force of gravity. We'll call that one FG1. All right, there's some forces. Now, of course, these forces of gravity are not causing the blocks to accelerate because they're on the floor. So um, let's draw our normal forces. Balancing here, 10 newtons here. We could start labeling these like FN1. This is balancing as well, 30 newtons. We could call that FN2. It's not going to end up being super important that we actually labeled these because we're going to talk about them in just a second, and we're not going to use them in our equations. But 50 newtons, normal force, Fn3. Okay, let's talk about these gravity and normal forces. They are balancing out on each object, and there's no vertical acceleration, meaning that we have equilibrium. The forces are balanced in the vertical direction, and really the only acceleration that's happening is horizontally. So you will have a good amount of scenarios like this where objects are on a table or floor or something, and you don't have to worry about the vertical sum of forces or the vertical acceleration because it's just equilibrium here. It's just gravity and normal force. They're balancing out. They're the same amount as each other, and there's really not much to say there. We don't really need to do any math with that. But this is where, like angled forces, right when we had angled forces to split into components, we had to make sure that the x direction forces go into an x equation, or that we have those for a horizontal sum of forces, and the y direction forces, we can do a y direction sum of forces. So we don't want to be mixing them together. Just like with kinematics, when we had big five, we want to make sure that we're doing separate x and y equations. So our sum of forces in the y direction is not really going to be useful. We're not going to make use of that. We're also going to make a comment here that we're going to assume there's no friction. Otherwise, we'd have to use the normal force and look at normal force times the mu value and find kinetic friction. I don't think they'll really be giving you friction on these problems because there's enough to do between the tension in the strings and the acceleration of all the objects. There's enough sort of things to do without introducing friction. So maybe in concept, maybe there'd be, if you run into friction in one of these, it would be more of like a conceptual thing of like, if this happens where the friction changes, or there's more friction or less friction, how does that impact the acceleration of these objects, right? So you could consider like, what if the surface of the floor got more rough or less rough, and all of a sudden now I have some friction? Like, okay, so friction acts to the left, it's opposing the direction of motion, and how does that factor into things like slow down, speed up, right? And how much does the acceleration get affected from friction? I guess things are already speeding up or slowing down because we have this 18 Newton force that's acting. Okay, so we don't have to worry about friction, which means the only other force we need to mention is tension. I did not mean to rhyme that. All right, now we're going to draw some forces of tension. The main thing to comment here is every rope, the right rope and the left rope, both have some tension on either end. So the one over here is pulling on the 1 kilogram like that. And this other end of the rope is also pulling back on the 3 kilogram. And there's a specific reason I've drawn those arrows basically the same length as each other. The amount of force of tension in this length of rope or string, especially because we assume that it's massless, if the string had some mass to it, then it would be a bit of a different story. But because we assume massless strings or ropes, the amount of tension at any point throughout that entire length of rope or string is the same. Same thing over here. There's some tension pulling this way, like so, and some tension pulling this way. Now, I happen to know just from doing these sorts of problems that the tension in the right rope will be bigger than the tension in the left rope. So if you knew that off the bat, you could draw it like that. Otherwise, you could just, if you wanted to draw this, you could just draw the forces of tension and you could adjust them later if you needed to make them bigger or smaller. But yeah, so in each length of the rope, on the left rope and on the right rope, there are forces of tension pulling on the 2 blocks on either side. And those amounts of tension, even though the 1 kilogram gets pulled to the right by this rope, the 3 kilogram gets pulled back to the left by this rope, those are the same amounts. It could be like +2 and -2 newtons, or +3 and -3. Same thing here. Whatever amount of force is pulling the 3 kilogram to the right, that same amount of force is pulling on the 5 kilogram to the left, the 2 ends of that rope. Okay, and that's an important thing about tension. So the amount of tension, we mentioned this back when we first introduced the force of tension. The amount of tension in a given length of rope, string, or cable, assuming that it is massless, that amount of tension is the same. So we could call this entire thing here just FT1. And we could call this one FT2. Alrighty. Now we're all set up. So what we can do is we have options. We could do a sum of forces, and as we mentioned, we'll add this into our little problem summary here, is we're not really using a sum of forces in the y direction. We're not interested in that. What we are interested in is we will use the sum of forces in the x direction. We're going to look at what's going on horizontally, which means that both the applied force, let's just label it as an applied force, why not? A person pushes or pulls, I guess they probably pull here on this object. We'll call it FA. Need to be capitalized, but you can do capital subscripts or non-capital, doesn't matter. FA. All right. So we will use a sum of forces in the x direction. Applied force will factor into that from the 18 newtons, and both the forces of tension FT1 and FT2 are both horizontal as well. Now, we have an option. We could do a horizontal sum of forces for the whole system. We could do it for just the first object, or just the second object, or just the third object. Now, there's a bit of a really neat thing here, which is when we're figuring out where to start with this, or like what do I choose? Do I choose to do the sum of forces for the whole system? Do I choose to do a sum of forces for individual objects? We're going to start, and I'll explain why. We're going to start with the entire system. So let's do this. A sum of forces, and this is our first step here, or our first thing we can do. A sum of forces in the x direction for the entire system. So what you can do is you can subscript. You could do sum of forces x, and then you can do SYS for system. That just lets us know we are indeed doing a sum of forces and looking at the forces for the entire system. What that's going to be equal to is the mass of the entire system times the acceleration of the entire system. So we're going to treat all three of these sort of as one combined object. We're just saying, Here's 8 kilograms of total mass. We are going to be pulling it across the floor with an 18 Newton applied force. Okay. So when we do this, for this, FT1 and FT2, both of those forces of tension, are internal to the system. So let's explain that. When we treat the entire three objects as one combined single object, or we look at the system as a whole, the connection of like the rope connecting each object is part of the system. So everything in the image, everything in purple and green is part of the system, meaning the forces in the ropes or strings pulling on the objects within the system are internal forces. That tension comes from the rope and the objects themselves pulling and pushing on the rope, and the forces from the rope acting on those objects. Those are internal. They are part of the system itself. Things like gravity, normal force, or applied force here are external. They are from objects outside of the system, like gravity from the earth, normal force from the floor, applied force from the person pulling them. But tension is internal. So what does that do here? It means we don't yet know the force of tension. So if we were to start putting tension into our sum of forces here, we'd have 18 newtons of applied force, we'd have FT2, we'd have FT1, and we'd run into a problem of too many unknowns. We can't really solve for anything. If we want to find the actual acceleration and find the tension in both ropes and get these numbers, we would run into a lot of unknown values. We wouldn't know the acceleration yet. We wouldn't know FT1 and we wouldn't know FT2. We don't have those values yet. So we're gonna limit it to one of those variables. We're gonna solve for acceleration of the system, but we're not gonna use FT1 and FT2 yet. We will find those forces of tension. And the way to avoid using those is to look at the whole system. If we do a sum of forces for the whole thing, what that means is tension in the ropes is acting from inside of the system, and as an internal force, we do not include it in the sum of forces. So this sum of forces ends up looking like this. It is only the 18 Newton positive applied force to the right, and that's it. If there were friction horizontally, we would include that because friction would be from the table, which is outside of the 3-block system. They'll often use phrases like the block system or the 3-block system or something like that. So the only force acting horizontally from outside of the system is our 18 Newton applied force. Now we want to make sure we use the mass of the entire system, 1 plus 3 plus 5. I think I said that number wrong. I said 8 kilograms earlier. It is not 8, it is 9. That is the correct number. So 9 kilograms, thankfully I caught that here, is the mass of the entire system. So just adding them all together. We assume no mass for the rope or strings, so 5 plus 3 plus 1 is 9 kilograms. All right, we are now exactly and perfectly set up to solve for the acceleration of this system. So that's our first thing we're going to get here. Pretty simple to solve. Do this. Keep in mind that newtons divided by kilograms does give you meters per second squared as a unit, because that is how newtons work. Newtons are kilograms times meters per second squared in terms of units. So if you divide newtons by kilograms, you get meters per second squared. And positive 2 meters per second squared is exactly the acceleration we get. So we have found the acceleration of our system. Now, we might say, hold on, I thought we were supposed to find the acceleration of every single object here. It said find acceleration for all objects. Have we done that yet? Well, the answer is yes, we actually have. Because once you find how much this entire system is accelerating, this is going to be the same amount for all of those individual objects. All of our objects. And that makes good sense because if the entire thing connected by ropes with the ropes pulled tight and the applied force accelerating everything off to the right as you pull all three objects together, tied together, you pull them off to the right. Sure, if you didn't keep a constant force, if you pulled a bunch and then you let off a little bit, then the ropes would go slack and some of the objects would keep sliding forward or bump into each other. There'd be other things going on. But if you maintain a constant 18 newtons of force and you just keep pulling with that amount, with a nice smooth value of acceleration that stays at 2 and doesn't change, then every individual object in the system had better also be accelerating at 2 meters per second squared. Because imagine if the back one, let's say the 1 kilogram, if that was accelerating less than 2 meters per second, in order for that to happen, like the string would have to break or something, and then the 3 and the 5 would keep accelerating at that same rate, but the 1 would fall behind or have less acceleration. If the 1 was accelerating faster than the 3 and the 5, it would start like catching up, and then you would lose the tension in the rope, because if it's accelerating faster than them, it's going to like and eventually run into the 3 kilogram. But the other problem is if it starts accelerating faster than the 3 and the 5, um, it's just going to lose tension in the rope. As soon as the 1 would accelerate more than the 3 and 5, your rope goes slack and you lose that tension. And the problem there is the tension is what provides the force for the 1 kilogram to accelerate. So this is a connected system where it wouldn't make any sense for the individual objects to be accelerating more or less than each other. So that 2 meters per second squared we just found, that is the exact acceleration for every single object in the system. That's a really nice help for these sorts of problems. Is once you find an acceleration, maybe you could even start with like if you had the values and numbers to find the acceleration for the 3 kilograms specifically, and you found that, and you found it was 2 meters per second squared, you can now apply that same acceleration to the other objects and to the entire system as a whole. So we found the acceleration of the whole system, again, treating them as one sort of combined 9 kilogram object experiencing the one external force of applied 18 newtons. We found the acceleration to be 2, and that is true the same amount for all objects. Okay. And so we'll operate under that assumption and we'll go forward using acceleration equal to 2. All right, let's take them one by one. I'm going to start with the 5 kilogram object. And the reason I'm going to do that is we're going to look at forces acting on individual objects now. And I already know one of the forces acting on that object, which is applied force. So for step 2, we are going to do a sum of forces once again. And now we're going to sum forces in the x direction for object number 3. You can do any sort of subscript there just to indicate I'm doing a sum of forces for this object. We're going to do mass number 3. So we do have to be careful with F equals ma. When you do a sum of forces for a particular object and you say, I want to look at the forces acting on object number 3 or object number 2 or the system as a whole, you want to make sure that the mass, the m in the F equals ma, that is the mass of whatever object you are looking at. If we sum forces for the system, we use the mass of the whole system. If we're summing forces for object number 3, we use the mass of object number 3. So make sure you line up those masses correctly, because if we're looking at the forces acting on this object, we better use the mass of that object to determine its acceleration or to look at whatever we're trying to find here. Okay. Now, I'm going to draw a free body diagram. I didn't really bother to do one for the system. You sort of could do it. You could draw one box or one dot, and that represents the whole system, all 9 kilograms in all 3 boxes. But it would have been a simple free body diagram. I guess we could have included gravity and normal force, but the 18 Newton applied force was the only one we really bothered with there. Okay. Let's look at, and Now that we're on to individual objects, we really had to be careful with internal external forces when we looked at the whole system because we didn't want to include tension in this sum of forces for the first one. But now that we're on to individual objects, the only internal forces we would worry about would be like, again, the molecules in this block holding on to each other. But we never really worry about that anyways. So those internal forces, they're not going to show up in our sum of forces, and we don't have to really think about them. Instead, we're going to draw a quick free body diagram for this. So let's do that over here. Here's object number 3, or mass 3. Now I could draw normal force and gravity, and if you want a full, complete free body diagram, sure, you could do that. In fact, I probably will. I'll do it a little more to the side so I have some vertical space here. There's mass M3. We got some normal force and gravity. That was, what, 50 newtons, so we'll make them pretty big. Normal force, Fn3, gravity, Fg3. But as we stated before, those don't really play a role here in terms of we're not going to do a sum of forces in the y direction. We don't really do anything with those. We have that horizontal applied force. So the applied force does pull directly to the right with an amount equal to 18 newtons. Now we're going to draw that tension Ft2. So the rope or string, this is the right rope or string as we see it. Ft2 is pulling to the left on our object number 3. There's Ft2. We could note that this should be a negative force. We expect that this should come out to be a negative number because it's pulling to the left, whereas applied force is pulling to the right. Also, it makes sense that the 18 newtons should be bigger than Ft2 because we expect that if our whole system and the objects within it are accelerating to the right, that acceleration being to the right means that our net force, our total force, needs to be the right. So we can think of it as the forces to the right need to win over the forces to the left and be larger so that the whole thing can end up accelerating to the right. Because we found that. We found that everything is accelerating 2 meters per second squared in the positive or rightward direction. Okay, let's put some things in here. So our sum of forces, we need to look at our free body diagram and say the horizontal forces are Fa plus Ft2. Those are the horizontal forces. No gravity, no normal force. Those are vertical. Equals M3A3. Okay, we will be able to solve for the tension Ft2 here because we know applied force, that is 18 newtons, positive 18. We're going to solve for Ft2. And then we know the mass. This is our 5 kilogram object. We're not doing the whole entire mass. We know the acceleration, which we got just up there, 2 meters per second squared. We found that was the acceleration of the system, and it's also the acceleration of each individual object within the system. Okay, so we can do this here. 18 newtons plus Ft2 equals 10. Now, kilograms times meters per second squared, the units here, that is newtons. Mass times acceleration, units of mass times units of acceleration do give us newtons. So we can just say 10 newtons. All right, last step to isolate and solve. Subtract 18 newtons from both sides. Get rid of it there. And our force of tension, Ft2, is negative 8 newtons. Now, we could note, based on our picture above, that if we look at Ft2 for the 3 kilogram object, that should be a positive force because that is pulling to the right. But we already identified that one of these is positive, one of them is negative. So this is going to be like negative 8 newtons pulling on the 5 kilogram object, positive 8 newtons pulling to the right on the 3 kilogram object. So the magnitude of Ft2, of that tension, is just 8 newtons. There's 8 newtons of tension in the rope. It just happens that it pulls to the left on the 5 kilogram object and pulls to the right on the 3 kilogram object. Okay, we've got one of our forces of tension. Let's go find the last one. So last step here we're going to do is we're going to move right on down the line, and we're going to sum forces for object number 2. Do a horizontal sum of forces. For object 2 equal to the mass of object number 2 times the acceleration of object number 2. Let's get a free body diagram going over here. Here's our object M2. We've got some gravity and normal force, 30 newtons this time around. Well, I guess we don't have to write the amount. You can if you want. If you want to label amounts and numbers on free body diagrams, feel free if that's helpful. Absolutely do it. Normal force and gravity, Fn2, Fg2. And we've got our tension. So this is actually the tension we just looked at. For object number 2 in the middle there, we've got force of tension Ft2. And I'm just coming up with these subscripts, whatever works to differentiate tension number 1 from tension number 2. So again, we'll double check our image up here. Ft2 is pulling to the right on object 2 in the middle with the 3 kilogram mass. Tension in the first rope, Ft1, is pulling to the left in the other direction. So we got to throw that on our free body diagram. Keep in mind those tensions are no longer internal, because when we look at specific individual objects, the tension is acting from outside of that object. If we look at the system as a whole, then tension is internal to the system. If we look at the objects by themselves, tension is external to the object. The rope is outside of the object itself, acting on the object. All right, so there's the key differences. We do include tension when we sum forces for individual objects. We don't include the tension in the sum of forces when we do it for the whole system. Okay, let's set up our sum of forces. So we've got horizontal forces, Ft1, Ft2. We've got, I must be nearing the end here. All right, we don't have too much longer on this part. Equal to the mass number 2 times the acceleration 2. All right, let's plug in some values. Ft1 is what we're going to find. We don't know that one yet. We don't know the tension in the left rope. Plus, we do know Ft2. And now in this case, it's positive. It was negative when it was pulling on the biggest object. It was negative. Now it's positive. This is a positive 8 newtons of tension, equal to the 3 kilogram mass of the object times the 2 meters per second squared of acceleration that we had established was the acceleration for all the objects in the system. Okay. Well, this is a pretty quick math here. We got 6. 3 times 2 is 6 newtons, equal to 8 newtons plus Ft1. Subtract 8 from both sides. And over here we have tension Ft1 equal to negative 2 newtons. Once again, this is only negative here because the tension in the left rope, Ft1, is pulling to the left on the 3 kilogram object, mass 2, and it's pulling to the right on the 1 kilogram object, mass number 1. So it's negative here because we're looking at the side of the rope that is attached to the middle object, and it's pulling to the left. It's pulling negative on this particular object. So that's why we got negative, just like we did up here. All right, again, absolute values is good to keep in mind because the absolute value of this tension is 2 newtons in the left rope and 8 newtons in the right. Now, there's one last thing we could do. I'll leave this up to you. Like, you could do it on your own time if you want to. It's up to you. You could do that last sum of forces, which is we could look at the 1 kilogram object. Now, the only force horizontally that acts on the 1 kilogram object is just Ft1. Also, I kind of went over it quickly with the 3 kilogram, you might be wondering, why didn't Mr. Byros draw the applied force for the free body diagram on object number 2? The answer is this. The 18 Newton applied force, this person who's pulling, they are pulling directly on the 5 kilogram object. They are not pulling directly on the 3 kilogram object. The tension FT2, pulling to the right from the rope, that is because of their 18 Newton force. So indirectly, the person is affecting, the person is resulting in a force of tension, FT2, that is acting on the middle object, but the person is not acting or pulling directly on the 3 kilogram or the 1 kilogram objects. So when we go individually and look at just the 5 kilogram object, just the 3 kilogram, just the 1 kilogram, we need to make sure that the only one of those that we would include this applied force in the free body diagram and in the sum of forces is just the 5 kilogram, because that's the only one that is directly experiencing that applied force of 18 newtons. So we do not include the 18 newtons in the free body diagram or sum of forces for the middle object, and we would not include it for the left object. The only force would be FT1 acting on the left object pulling to the right. And you could do a real quick check because your sum of forces would just be, well, 2 newtons, because that's the tension in the left rope. It would just be 2 newtons pulling on a 1 kilogram object. And if you did that math quick, you would find it does result in the same acceleration. That'd be a way to check your work. We have all the values we came for now, but you could check your work and say, okay, this last tension, FT1, pulling on the smallest object, that better result in a 2 meter per second squared acceleration, because we said the acceleration should be the same for all of these objects. Okay, now you're not always going to have numbers, right? In fact, in AP, there might be less numerical problems than deriving or comparison problems or conceptual things or other types of questions that don't directly involve numbers as much. But I think this is a good way to just go through and say we could use a sum of forces for the entire system, like we did here. That is most useful for eliminating internal forces like tension. We don't have to deal with them when we do this sum of forces. And then it's very handy for looking at that acceleration. Because if you have the forces besides tension here that are acting externally on the system, that would just be our applied force. And if you know the mass of the system, or you have at least variables and something to work with for what the mass of the system is, you can then look at that acceleration. And once we have that here, it really carries over into the rest of the problem because it allows us to individually look at the objects by themselves and know that their acceleration in a connected system is the same as that acceleration we found. This allowed us to look specifically at tension pulling on the big object or the medium object and find what those forces of tension were by using the sum of forces. And it's just a good reminder that we're not always solving for like mass or acceleration or something. Sometimes we just find one of the forces. We say, well, our sum of forces is these two forces. I know what one of them is. I know what the mass is. I know what the acceleration is. I could solve for one of those forces. So Newton's second law is also just useful for finding forces. If you know the mass and acceleration and you know all of the forces but one, you could then isolate and solve for that one force. So lots of uses there for finding acceleration or mass or finding one of the forces. Okay, we're going to try to squeeze in Atwoods machines here because I want to try and cover everything that is on your quiz. So when we get to the Unit 2 quiz, it'll be up through Atwoods machines. So now I have to just remember how to do a new page. It usually prompts me to do this, but well, I guess I could cheat the system and try to draw a bunch of elements, and maybe it'll tell me once I reach my limit. We're just gonna do that. Oops. Or not. All right. Well, oh, I think this could be it. pages. New one. Haha. I've done it. All right. Let's look at Atwoods machines. Although now I need my... There we go. All right. Atwoods machine time. So what is an Atwoods machine? Well, it's a type of system of objects. Okay. Atwoods machines are a particular type of system of objects. Consisting of two or sometimes three, but usually two objects connected by a rope or string which passes over a pulley. Okay. There are a few variations. Um, which we will draw. We'll get to those in a little bit. Okay, cool. Now, there's a few things that are important. So, importantly, the following. First of all, I'm going to go ahead and let's see. We're going to do just like a few of these sort of bullet points, and then I'm going to go ahead and draw a example of an Atwoods machine so that we can have something to go off of, because I don't want to just tell you what's important without having some image or reference to look at, because that's going to be helpful. So I'm going to draw like a, and leave myself enough room. Good here. Draw like a ceiling or something. Again, there's some variations on this, and we'll draw what they are, but here's a pulley. And while we're at it, we'll mention there's usually no friction. If there is friction, we'll talk about that in a second. Okay, there's our pulley. We've got a rope that passes over it. I'm going to draw that in blue here. There's the rope going over the pulley. And we got two objects attached to the rope. We'll draw those on the end here. One object here, that. Object number two like that. All right. And then the first important thing that we're going to point out about these Atwoods machines is that we're going to define positive or negative directions. And we're going to define those positive and negative directions not as up, down, left, right. It's something weird. We haven't done this before. So up, down have been, we've said like up is positive, down is negative, or left is negative, right is positive, etc. Instead of doing that, we're going to define them not as up, down, left, right, but as clockwise and counterclockwise. Let's go down to our image and inspect it. So what that means is we've got some forces acting, and we could draw them pretty quickly. There's not a whole lot here. Like our bigger object has a nice big force of gravity. We call it FG2. Our smaller object has some smaller force of gravity. We'll call it FG1. And then we've got some tension. So there's a tension here. Tension in the rope like this. Tension in the rope like this. And you'll notice I drew those the same size because, as I mentioned before, tension in a given length of rope, string, or cable is the same amount. So because this length of string connects both objects and just runs over the pulley, that length of the string will have the same amount of tension all throughout it. So the tension pulling up on the right object is the same as the tension pulling up on the left object. Okay, now the key here is we're not going to say something like both forces of gravity would be negative and both forces of tension would be positive. That might be if we were doing down is negative, up is positive, we would do that. But the reality is saying both forces of gravity are negative would mean that both forces of gravity are trying to do the same thing with this system, but they're not. The force of gravity FG2 is trying to get the whole system to accelerate clockwise around the pulley, right? Because if FG2 has its way, the right object goes down, the left object goes up, and we probably know from an intuitive understanding of this that that's what's going to happen. The heavier object will go down, the lighter one will go up. So FG2 will succeed in doing that. FG2 will successfully cause the whole thing to go clockwise around the pulley. It's going to result in a clockwise acceleration. FG1, on the other hand, if FG1 had its way, or if FG1 was the bigger object and the bigger force of gravity, that would then successfully get the whole thing to go counterclockwise around the pulley. So FG1 and FG2, and also we could say those forces of tension for the one object versus the tension for the other, they're really trying to do opposite things, right? FG2 is trying to get this clockwise movement, and FG1 is trying to get the counterclockwise movement. So that's why we define clockwise and counterclockwise as our positive, negative directions. So we'll go ahead and do a quick definition there. We'll say, now you can do these if you want, but we're just not going to use up, down, left, right. You can draw this sort of completed version. Now you get to see the full version. Something like this. So this is like, eventually we will have problems where up, down, left, right matter, but clockwise, counterclockwise also matter. So the little image I like to draw is up is positive, right is positive. Not that we're going to use those here. Those aren't really relevant. But you can also include this to say clockwise is positive. If I wanted to say counterclockwise was positive, I could draw an arrow with the arrow going counterclockwise and say positive. So this tells you up is positive, right is positive, but we're not going to use those for Atwoods machines. The key one here, you could just draw this, some sort of a clockwise arrow, and say that it's positive. That would be fine. But yeah, the key here is that clockwise is the positive direction. So we could note something like this is a positive force. It's trying to get everything to go clockwise. This tension up here, the tension pulling up on the left object, that's also going to be a positive force. This one's trying, FG1 is trying to get everything to go counterclockwise. That's going to be negative. This tension pulling up on the right object is also trying to get a counterclockwise. That's going to be negative. So I'm just putting in parentheses, a couple of these forces are positive, a couple of those forces are negative. Okay. Now, if we did have friction here, friction would oppose the clockwise acceleration. So this would be, we could draw it like this. Friction would be drawn as like a counterclockwise curved arrow. That would be force of friction kinetic. If we have it. Most of the time, we're not going to see friction, but if you did have friction, the way you would incorporate that into the positive negative thing is friction here would be negative. It'd be counterclockwise because it's acting against the direction that the objects will actually go, right? FG2 is bigger than FG1, so it will successfully cause everything to accelerate and go clockwise around the pulley. FG1 is negative, and friction would also be negative if there were friction, because the friction from the pulley would be trying to resist that clockwise motion and would be going counterclockwise. So everything that's positive or negative that we put into our sum of forces is just positive or negative based on whether it's trying to get everything to go clockwise or trying to get everything to go counterclockwise. All right, so that's our first important thing. We define positive and negative directions as clockwise or counterclockwise. Now, this one we already mentioned before, but we'll mention it again because it is important for any system of objects connected by a rope. The force of tension in a section of rope or string is the same throughout. In a section of rope or string, or even something like a cable, is the same throughout. All right, a couple more things for Atwoods machines. Once again, when considering the system, and this is just a good reminder from our last problem as well, when considering the system as a whole, tension Ft is an internal force. All right, and lastly, if friction acts on the pulley, it opposes the direction the objects would move. Because that's how friction works, right? Friction goes against the motion of an object or opposes the direction it would move. Okay, so I'm not going to do a full problem here. I think in class or at some point we will do like examples with Atwoods machines where we're looking at, okay, I could sum forces for the entire system. In that case, you'd have like FG1 and FG2. Those would be external forces of gravity, but tension would be internal when we look at the system. If you had friction, you would get force of kinetic friction acting opposing the direction that they're going to move, and friction would be an external force. You could think about the system as the two blocks in the string. So this is just a classic Atwoods machine here, and we'll just put like this is sort of your basic Atwoods machine. Your basic Atwoods is going to be like, and it's thought of as like a block spring. Block string system or rope or whatever it is. This is often how AP will write it when it comes to systems. They'll just write all the things in the system with dashes in between them. So there's two blocks and a string, so they call it a block string system. They're not always going to do that, but it's a common way that they write it. So this is your basic Atwoods block string system over a pulley just like this. But notably, the pulley is not part of your block string system, so friction would be an external force that you would include for the system. So I'll just make a quick note here, right? Your sum of forces for the system would include FG2, FG1, and friction if it exists. Friction if it's there. It's not, of course, it's not always going to be, right? Friction is like Depends. A few problems will have friction in it, but for the most part, you won't really encounter that hardly at all. So don't expect a ton of friction in your problems. All right, so friction if it's there. Okay, let's briefly run through individual objects. Again, we're not going to do a full problem or anything like that, but if you sum forces for object number one, I guess we should identify that. We'll have this one be one, this one be two. Sum of forces for object number one. And you can also indicate if you want, it's hard to draw here, but you could do a little clockwise, counterclockwise symbol to say, I'm doing a sum of forces for the system in the clockwise, counterclockwise direction, just to remind yourself that positive and negative are based off of clockwise, counterclockwise. Sum of forces for object number one would include, looking over here, we've got the force of tension Ft acting on object number one and the force of gravity Fg1. Friction from the pulley would affect the individual objects through how much tension there is or something like that. But the friction itself from the pulley does not act directly on object number one. It acts from the pulley onto the rope, which is part of the system. So we would include friction for the system if it shows up. We would not include friction for the individual objects. And object number two, if we sum forces for object number two in the clockwise, counterclockwise direction, that would be the force of tension from the rope pulling on object number two up here. We've kind of already got a sort of a free body diagram for it. And then Fg2 also acting on it. So, and you could do exactly the same sorts of things we did in the previous example with systems where we like find the acceleration, or we could look at what the force of tension is by individually, because you can't use the sum of forces for the system to look at tension, because tension is internal, not included there. But you can use individual objects and their sum of forces to look at and find tension or to work with tension. So it's really just, if you want to avoid doing anything with tension, then do a sum of forces for the system because it doesn't have tension in there. If you want to find tension or work with it in some way, do a sum of forces for one of the two objects because they would include tension. Okay, we're going to close out with just a couple of variations on Atwoods machines. Again, we'll spend some more time with this through like problems in class or maybe some examples or other things. But we're just going to close out with some variations on Atwoods machines. And we'll just make a couple key notes about each one. They're mostly the same in terms of like for the system, when you sum forces, you don't include tension, et cetera, et cetera. They're in large part the same, but we'll point out a couple things about each one of them. The first one is going to be like a table. So if you have a table like this, and you've got a pulley on the edge of it, and then you're going to have like one block on the table with a string. Let me do my string in blue again, just so I can separate that out. String attached like this over the pulley, your other object hanging off the edge. Now this one's interesting because you could actually have a really small object here. It also could be really big. We don't really know, but you could have an object on the edge that's smaller than this. And because there's pretty much always no friction, I mean, unless if you were told there was friction on the table, sure, we could like account for that. But usually there's no friction on the table, which means you'd still have, for relevant forces, you'd still have object number two and the force of gravity Fg2 like this. So there's your force of gravity Fg2. You'd still have some amount of tension in the string, and that tension would be the same amount pulling here as it is there. The tension on object number one and the tension on object number two is the same as each other. So there's Ft. It's also just Ft, the same number or amount, even though one pulls clockwise and one pulls counterclockwise. So this would be like a positive. If clockwise is positive, this would be a positive force of tension. That would be negative, but they're the same amount. And that would be it, honestly. This one actually gets a little more simple because we might wonder, like, what about FG1? What about the force of gravity on object number one? Does that not matter? Well, it turns out for the clockwise, counterclockwise direction, it doesn't matter because for object one sitting on top of that table, the force of gravity, FG1, on that object is exactly balanced by normal force, and neither gravity nor normal force will contribute on that object number one. Neither one will contribute in any way to the clockwise, counterclockwise motion of the blocks moving around the pulley, clockwise or counterclockwise. So we don't have to worry about FG1 or the normal force at all when we're summing forces. So in some ways, this is more simple. If there were friction on the table itself, this would be like your force of kinetic friction on the table if it's present. Usually not. But that would be pulling over the other way. Because as the thing with this is there's really only one option. I guess if you grabbed the object on top of the table and pulled to the left, you could get the object two to go up. But if you just set it up and let it go, really the only option is the weight and the force of gravity from object two will cause the whole thing to accelerate clockwise around the pulley. Okay, so that's one variation. The other one involves ramps, so I'm very briefly going to mention it for when we see ramps later on, but we haven't done ramp stuff yet, so we're not going to worry too much about that just yet. There's this, there's the pulley. All right, let's do one block on the ramp. And another one hanging off the edge. We'll do our string or rope here. And then boom, like this. Okay. Oops, was not as good as I would have hoped. Let's do it again. One more try. Okay. We've done it. Okay. We can identify objects 1 and 2 again. We'll talk a little bit about some of those same forces. Like here's object 2. Still got a force of gravity, FG2. We still got some tension going like this, pulling on this string, and the same thing over here, some tension like that. Those are your forces of tension, FT. Same amount of tension here, FT as well. Now, there's some stuff with gravity, which does act straight down towards the center of the Earth. For now, we're just going to say there's some ramp stuff that we'll do. We're not going to get into it right now. Ramp stuff with the force of gravity FG1 for this object that we will label number 1. So object number 1 does have a force of gravity. It's not like the tabletop one. The ramp one is a little weird because the tabletop we just get to ignore here. So we just simply don't use that force of gravity FG1. We're not going to encounter it at all. But with the ramp one, we do use force of gravity FG1, but there's some stuff we have to do with it for the ramp. So over here we don't use FG1. We just don't need it for the sum of forces. It doesn't affect the clockwise, counterclockwise motion of the objects around the pulley. Okay, but yeah, the ramp stuff we'll do later. We'll figure out how to deal with force of gravity on an angled, inclined plane with a ramp, and these ones would get kind of complicated because the ramp stuff is already just kind of complicated, and you hopefully won't see too many of those. But the one variation you definitely could see would be the one on the top of the table with the one block hanging off the edge over the pulley. So yeah, those are Atwoods machines. 2 objects. It's a system. 2 objects. It could be 3. Actually, I'll mention real quick with this one. You could just put another block on the table, and that's most often where you see 3 together. If you have 2 blocks on top of the table connected with another string one gets connected to three, I guess, over on the left. That's how you would get three total objects in an Atwoods machine. But most of the time, it's two connected together by that string or rope over the pulley. Okay, so all about systems of objects today. We did how to solve with systems of objects. We did like the three connected together. It could be three with a rope. You could also get three kind of stacked up next to each other, right? So you could have the three boxes kind of bumped up next to each other, and you're just pushing all three of them together across the table. You might see that one as well. But then we went specifically into Atwoods machines and looked at the counterclockwise and clockwise piece of things, but still a very similar process of choosing, do we want to sum forces for the whole system here, or do we want to look at individual sum of forces for individual objects, and then a couple of these variations or different Atwoods machines you could see. All right, we're gonna call it there, and hopefully it didn't go too terribly long. I wasn't tracking time too well, but I wanted to get through Atwood's machines so that this is the kind of stopping point for the quiz. This is the last piece of material that will get covered on your quiz. Okay. Well, I hope you have a good one. Don't forget to use the Padlet if you have questions, because there's lots of things going on here and lots of questions that could be asked. So please ask your questions and check in class. We'll do problems. We'll do examples. You'll get to do some problems yourselves. We'll try and figure out how to be applying these systems of objects tools in our problems. Okay, we'll see y'all in class.